Okay, so what is this thing really? Well, at its most basic, a centrifugal compressor grabs a gas and, using just incredible rotational speed, it ramps up the pressure like you wouldn't believe. It's not just pushing the gas. Think of it more like it's supercharging it, packing all those molecules tighter and tighter together. And that one transformation, it's absolutely essential for, well, countless industrial processes.
And when I say essential, I am not kidding. We're talking about the things that make our modern lives work. The gasoline in your car, the electricity lighting up your home right now, even the plastics in your phone and the AC that keeps you cool on a hot day. Yeah, these compressors are the hidden engines behind all of it. They're everywhere, even if you never see them.
All right, so here's the game plan for today. First, we'll tackle how it all works. Then, we'll get into the guts of the machine, the rotating heart and the stationary skeleton. And to wrap it up, we're going to look at something really critical, how to troubleshoot compressor surge. Let's get into it.
First up, how does this thing actually work? I mean, how do you turn simple speed into massive amounts of pressure? It turns out it all comes down to a really cool and surprisingly elegant principle of physics.
So here's the core idea in a nutshell. The whole process is really just a brilliant act of energy conversion. You take kinetic energy, that's the energy of motion, right? And you give a ton of it to the gas particles. Then, the clever part is how the machine transforms all that speed back into good old-fashioned pressure. Okay, so it all starts right here, at what's called the eye of this wild-looking, rapidly spinning wheel called an impeller. The gas gets sucked right into the center, and this is where the magic really begins. You see those curved blades? They act a lot like airplane wings, creating a pressure difference that basically pulls the gas in and then just starts slinging it outwards with incredible force.
So as that impeller is just whipping around, centrifugal force takes over and flings the gas particles to the outside at unbelievable speeds. Now, once the gas leaves the impeller, it's at its absolute fastest. From there, it flies into a stationary part called the diffuser. And if you look, you can see the diffuser is designed to get wider. That forces the super-fast gas to slow way down. And here's the payoff. As that speed, that velocity drops, all that kinetic energy has to go somewhere, and it gets converted directly into pressure. Boom! That's the principle in action.
Okay, so now that we know how it works, let's look at the actual parts that make it happen. We'll start at the very core of the machine with the rotor assembly. This is the collection of all the parts that spin together, the real rotating heart of the compressor.
So, we've already met the star of the show, the impeller. That's what does all the heavy lifting of accelerating the gas. It's mounted on the main shaft, which is what transmits all the power from the driver, like a motor or a turbine. But check this out. There are two other components here that are absolutely critical for the machine's survival: the balance drum and the thrust bearings. Their whole job is to manage the insane forces being generated inside this thing.
And this right here shows you exactly why those last two parts are so important. Think about it. You've got this massive pressure difference from the front of the impeller to the back. That creates a gigantic force, we call it axial thrust, that is constantly trying to shove the entire spinning rotor sideways. So how do you fight that? Well, engineers came up with this brilliant solution called a balance drum. It actually uses the compressor's own high-pressure gas to create a perfectly opposing force, which cancels out most of that thrust. It's what keeps the machine's super delicate bearings from getting, well, completely obliterated.
All right, so that's the spinning stuff. But of course, the rotating assembly doesn't just float in midair. It's all housed inside a really complex set of stationary parts, the non-moving bits, that basically form the skeleton of the machine. And their job is all about expertly guiding the gas flow. Yeah, this cross-section shows it perfectly. You see, after the gas leaves one impeller and gets pressurized in the diffuser, it's often not done. For more pressure, it has to be guided smoothly to the eye of the next impeller for another round, another stage of compression. That's what these stationary return passages do. They're like these perfectly shaped aerodynamic channels that make sure the gas doesn't lose energy and gets to the next stage as efficiently as possible.
And even with these stationary parts, you've got some really key design choices to make. For example, that diffuser we talked about, it can be vaneless, just a simple open space. That design is super stable across a wide range of flows, but it's not the most efficient. Or you can put vanes in it, which act like little wings to recover pressure way more effectively. The catch? Those are only really efficient inside a very narrow operating window. It's that classic engineering trade-off, right? Do you design for broad, rugged stability or for absolute peak performance?
So, what we've got here is this incredibly delicate dance, a balance of moving parts, stationary parts, all managing these immense forces. But what happens when that balance gets totally thrown off? Well, that brings us to the danger zone. We're going to talk about the single most dangerous condition a compressor can face: surge.
See, this whole operation relies on one thing, a constant forward flow of gas. It has to keep moving. So, what happens if something downstream, like a closed valve, blocks that flow? What happens when the compressor is still spinning like crazy, trying to build pressure, but the gas has nowhere to go?
This is the crucial point. For any amount of pressure it's making, a compressor needs a certain minimum amount of gas flowing through it to stay stable. That limit, you can see it on this map, is called the surge line. If the flow drops below that line, well, the impeller just can't win. It can't push against the huge wall of pressure it's already built up, and the result is catastrophic. The high-pressure gas downstream suddenly reverses direction and just slams backwards through the entire machine. It's violent.
And no, this is not a gentle process at all. Surge is basically a series of violent, rapid-fire explosions of gas reversing course. The consequences are, well, they're severe. You get extreme temperature spikes from all that churning gas, massive vibrations that shake the whole unit, and that rotor gets slammed back and forth, destroying the thrust bearings. A single surge event can damage seals and bearings in just seconds, and if it's not stopped, it can lead to the catastrophic destruction of the entire rotor. It's that serious.
So, obviously, you have to prevent this disaster. That's why big compressors have what's called an anti-surge system. Think of it like a safety net. It's a control loop that is constantly watching where the machine is operating. And if it even thinks about getting too close to that dangerous surge line, a valve automatically pops open. What does it do? It recycles some of that high-pressure gas from the outlet right back to the inlet. This creates an artificial flow, basically tricking the compressor into thinking everything's fine, and that keeps it operating safely away from the danger zone.
So when you really look at it, a centrifugal compressor is just an absolute marvel of engineering, isn't it? It's a machine that's designed to tame just incredible speeds and pressures. But it's all built on this delicate balance of immense forces. And as we've seen today, understanding how all those parts, the rotating and the stationary, all work together, well, it's not just some academic exercise. It's the absolute key to harnessing all of that incredible power safely and reliably, day in and day out.